really the only session that we're going to concentrate on probability. For the most part, we're going to be going back immediately next week to looking at distributions, how data is distributed, normal distributions, and so on and so forth, and how we can interpret them mathematically. So there's going to be some elements here that are going to be important, but most of it is kind of isolated from what we're going to be doing the rest of the semester. So don't get too hung up on some of these things. If you have a problem with it, I'll let you know which parts of it are going to be important to you. Matter of fact, probably if you see me start to emphasize things, is because I think I'm trying to suggest to you there might be things that come up later on. Do we take breaks online like we do in class? Normally in the other labs, we were only doing this for, we were only on for maybe an hour or so. This one's going to be a little bit longer than that. So I'm going to propose that we do take a short break about midway through so that you can take care of things, charge up your batteries, or do whatever else needs to be done. Okay, so let's consider that we will do that for a moment. In fact, if I forget about it, you can remind me at some suitable time, like maybe about 7:30 or 7:45 or something like that. Okay, so let's delve into this. Let's take a quick look at this stuff. First of all, we're talking about chance events, probabilities. And I'm going to give you an example. I'm going to start with a very simple example. You guys know that if you flip a coin, the chances of it being heads or tails are 50% or 0.5. Half of the time it'll be heads, half of the time it'll be tails. Okay, now if I flip a second coin, that's an independent event. The coin doesn't know whether the previous coin was a heads or a tails. So if I flip it a third time, that third coin toss is an independent event, and it again doesn't know what the first two outcomes were, so it's 50% again. Now, the probability of getting two heads in a row is going to be 50% times 50%, or 0.25, or in other words, 1 in 4. Okay, that may be intuitively obvious to you, may not be. The probability of getting three heads in a row is going to be 0.5 times 0.5 times 0.5, which is equal to 0.125, or 1/8. Or in other words, there's one chance in 8 of that occurring. Each one of those events are independent events. That's why that multiplication rule works. If they're not independent events, that multiplication rule is not going to work. We're going to play around with this a bit and get a feel for the events that are independent and events that are not independent, where one event has some dependency on the other event. Okay, so I'm going to start out with another kind of independent event. We're going to come back to that coin toss at kind of at the tail end of this first part of the exercise. Okay, so let's take a look at what we have here. Let me blow this up a bit. Okay, let's say I have a population of males, maybe Hunter graduate students, male Hunter graduate students, and I know that the probability that an individual that I pick out from Hunter College, there's a 50% chance that this individual is going to be male. This may or may not be true. Based on my experience with at least the graduate school and stuff like that, I think that that actually there's more females than males. So the probability that I would pick out a male if I randomly selected a person from the graduate students at Hunter, and they would that they would be male is probably a little less than 50%. I'm going to change that to 0.4. Maybe 40% of the students are male, 60% are female. Make it a little bit more realistic. Okay, so now the chances of my picking an individual and their being male is 40%. In other words, if I picked one person, I would expect that there's a 40% chance it'll be male. If I pick a second person, again, independent event, there's going to be 40%. I'm going to assume that if you look at this with replacement, the probability never changes based on people I've pulled out. So it's as if I put that person back into the population to be chosen. So it's never less than 40% probability. Okay, so let's take a look at another probability. What's the probability that any individual in his population is left-handed? And I'm going to assume for a moment that the probability that they're left-handed is 10%. Okay, so now that presumes that there's no difference between the rate of being left-handed for males and for females. And I have no reason to believe that there's a difference. If anybody here has ever read a study that suggests that there's a difference in the percentages of males and females that are left-handed, I'd be interested. But I'm going to start with the assumption that there's no difference. That if you're a male and female, it's the same 10% probability that you're left-handed or left-handed rather than right-handed. Okay, so now I'm going to ask you, we just learned about that multiplication rule where we have two independent events where one doesn't affect the probability of the other, that we just simply multiply the two probabilities to get the probability of them occurring at the same time. Okay, so the probability of being male is 40%, 0.4. Probability of being left-handed is 10%. What's the probability of being male and being left-handed if I picked an individual out? Anybody want to hazard a guess as to what that is? Multiplication rule? Right, 0.4 times 0.1 is equal to 0.04. Okay, 4%, right? Makes sense? Anybody take issue with that? Do you all agree with that? That if these are independent events, then I can say that the probability of a person being both male and left-handed is 4%. 4 out of every 100 people would be male and left-handed. I'm going to propose another situation. Okay, this is male, probability male, and left-handed, probability being left-handed. Okay, it's going to be that. Okay, so now let's say I ask you, what's the probability of being female and left-handed? Okay, anyone has? I want somebody to take a guess at this. What's the probability of being female and being left-handed in this population? Again, assuming that, okay, somebody suggested 6%. How do we get that 6%? Do we see how we got that 6%? Well, if the probability of being male is 0.04, since you have to be either male or female, right? They're independent and they're exclusive. You have to be one or the other. Well, probability of being female is going to be 0.4. 0.6. 60% of the females are of the students are female, times 0.1. Okay, is equal to, 0.1 is equal to 0.06. Okay, how about the probability of being female and right-handed? And the probability of being right-handed. Okay, somebody else give me a suggestion on that. Okay, 0.6 times 0.9, exactly right. Okay, so we know that probability of being female is 0.6, probability of being right-handed is 90% of the students are right-handed, so it's 0.9, so that would be 0.54. That's a likely outcome. More likely than not, the person's going to be female and right-handed rather than any of the other possibilities that exist. Okay, so that's our first look at independent events. Now, I'm going to give you another brief introduction to independent events, except I'm going to give it a little bit of a twist. I'm going to tell you that the probability of being a redhead is 20%, 1 in 5 people. The probability of being diabetic is equal to 0.05, let's say, in this particular population. If I told you I did a survey, I took 1,000 people, right? Took 100 people. And I said to myself, okay, out of this 100 people, I found that 5 people were both redheads and diabetic. Okay, well, that's 5 out of 100, so that's equal to 5% that meet that criteria. If these were independent events, what would I expect for an independent event? I would expect it to be 0.2 times 0.05, and that's equal to, that's going to be equal to 0.01, right? I would expect, did I get that right? 0.01, yes, right? So 0.1, no, 0.05, 10, 0.2. Oh, you're right. It's not 0.5 times 0.2, it's 0.05 times 0.2. Okay, so it would be 0.01. You guys agree with me? Isn't that what? Oh, I'm sorry. I didn't put that zero in there. Sorry. Whoops. Right. 0.5%. Right. I did it right down here. I didn't do it right up there. 0.05. So that's going to be 0.05 times 0.20. Right. It's going to be 1,000. Move the decimal place over 2 places, and it's going to be 0.01. Okay. So now, or 4 places. So now there's a 1% chance of being diabetic, right? So, in fact, I found when I actually surveyed, let's say the entire population was 100 people. Let's say we actually did this with 1,000,000 people. We sampled an entire population, right? And we found that 5% of the population was both diabetic and had red hair, right? Well, since we know our probability of being redhead is 0.2, 20%, probability of being diabetic in this population is 0.05. Oops. Okay. What does this tell you that we found this result rather than the result 0.01? What does that tell you about the relationship between being redheaded and being diabetic? Anybody want to hazard a guess? What does that tell us? Redheads are more likely to be diabetic than others. Right. So what does that tell you? That tells you that these are not independent events, right? That in fact, redheads have a different rate of diabetes than the rest of the population does. Now, if I gave you these parameters on, say, a homework, and I told you, well, there's, in this population, 20% of the population has red hair, and half of, 0.05% of the population is diabetic. Then I told you that 5% of the population is both diabetic and has red hair. You know that there's something wrong here. It should have been 1% that would be both redheaded and diabetic. So they can't be independent events. Being redheaded makes you more likely to be diabetic, or it could be the other way around. Maybe being diabetic makes you more likely to be have red hair. Maybe they're somehow or other they're linked. So these are not independent events. If you want to test if an event is independent, you can check to see if the relationship holds up for that you would expect. That multiplication relationship holds up for the entire population. So it's an easy way, simple way to check whether two events are independent or not. Okay, so I'm going to take a look at another set of events. Let's say that the probability that a person is insured is 80%. You're going to choose one person from the population randomly, right? And it turns out that, okay, sure enough, that person, it's 80% chance, the probability is 80% that that person is insured. Probability that a person is not insured is going to be 20%. Okay, let's say we choose 3 people randomly from the population. What's the probability that all 3 are insured? Okay, well, probability, remember these are independent events. We're going to randomly sample the population. Chances are 80%. Next person, chances are 80%. Next person, chances are 80%. Chances that all 3 are insured is going to be 0.8 times 0.8 times 0.8. And Jensen, I think, put in that it was 0.512. I'm going to trust them, okay, and say that that's what the result there is. Okay, so 0.512 or 51.2% is the probability that all 3 would be insured. Okay, so now let's say we choose 10 people randomly from the population. What's the probability that all of them would be insured? Okay, this time you don't have to multiply it out. You can just tell me, right? It's going to be 8 to the 10th power, right? In other words, you're going to multiply each one of these times itself, 0.8 times itself 10 times, and that would be your probability. Probably easier to use Excel or a calculator to do that than to do that by hand. Now, what's the probability that if you chose 3 people randomly, that none of them would be insured. Right? Somebody hazard a guess for that? Well, a probability that one of them is not insured is going to be 20%. So the probability that 3 people are not insured is going to be 0.2 times 0.2 times 0.2. Okay, what's that going to be? That's going to be 0.04 times 0.2 is going to be 0.008. No, not mistaken, right? So we're going to get a probability of 0.008, if I got that right. 0.2 times 0.2 is 0.04 times 0.2 would be 0.008, or a little less than 1% chance that all 3 people would be insured. Well, I'm gonna throw a twist in here now. What's the probability that if I chose 10 people, that 3 would be insured and 7 would not be insured? Anybody want to hazard a guess to what that probability might be? It's kind of a trick question. That gets complicated, right? In other words, at first glance, you might say to yourself, well, let's see, 3 insured, 0.8 times 0.8 times 0.8 times 0.2, 0.2, and so on and so forth, right? But that's wrong, right? The reason why that's wrong is because we have a lot of possibilities here. We could have insured, 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 not insured, not insured, not insured, not insured, so on and so forth. We could have insured, not insured, 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 not insured, not insured. There's many, many possibilities here as to how these might be distributed. So it's a much more complicated issue that when we look at the outcome where there could be a different number of people insured and not insured, but we don't know specifically which of these selections are. In other words, we're only interested in that 3 are insured, 7 are not insured, but we're not interested in the sequence in which we pick out people that are insured or not insured. Just that when we get to 10, that we got 3 people insured and 7 people are not insured, that probability gets very complicated. We're going to learn about that in the next few weeks, and that's involves something called a binomial probability. Anybody know why it's called binomial? Give me a guess why you would call something like that a binomial distribution or a binomial probability. Okay, insured and not insured. Bi, right? 2. You have 2 possibilities. Either they're insured or they're not insured. They're male or they're female. They passed, they didn't pass. Exactly. You have 2 possibilities. That's a binomial problem. Okay, so we're going to deal with that in the future. We're not worried about that right now, but recognize that everything I've mentioned so far is situations where you could apply that multiplication rule until, except for situations where they're not independent, right? And situations where we're dealing with events where we can't use the multiplication rule because there's many other possibilities that are not accounted for by it. Okay, so now let's take a look at something that's kind of similar to this, except we're going to scale it down a little bit. Instead of looking at 10 people with 80% chance of being insured and 20% chance of not being insured, we're going to take a simpler example. We're going to take a coin toss. We're going to toss a coin 3 times in succession. I'm going to get a pad of paper here so I can do this on the pad. Okay, actually, I don't need this right now, this page right now, so I'm going to get this out of the way. Okay, let's see. Okay, so I'm going to start out with my coin toss. My first coin, I'm going to toss my first coin, and I got 2 possibilities for the outcome of that first coin. It can be a heads or it can be a tails. Right? That's my first coin, first toss. I got 2 possibilities there. Now on my second toss, if it had been a head, I got 2 possibilities for the second toss. One could be a head, one could be a tail. If it had been a tail, my second toss could have been either a head or a tail. Right? These are all equal possibilities because it's an equal possibility that the first toss would have been a head or a tail, right? And then the second toss didn't know what the first toss was, so it could be equally a head or a tail as well. So now on the third coin toss, right? Again, third coin could be a head or a tail. It could be, if this was our outcome before, it could be a head or a tail. And if this was the outcome, it could be a head or a tail. And if this is the outcome, it could be a head or a tail. Okay, so let's take a look at what we have now. Now, I'm going to take a look at my 3 coin tosses. Okay, let's look at the first possible outcome that I can have. Could be heads, heads, heads. So I'm going to write this down here. 3 heads, right? 2 heads, 1 head, right? Or 0 heads. Well, that's the same thing as saying no tails, right? I'm going to undo that. Okay, saying 3 heads is the same thing as saying no tails. 2 heads is the same thing as saying 1 tail, and 1 head is the same thing as saying 2 tails, and no heads is the same thing as saying I got 3 tails on 3 coin tosses. So let's look at all of the possible outcomes here. One outcome is I could toss a head, and a head. That occurs once, right? I'll put 1 tick mark up there. Could be a head, and a tail. That's 2 heads. That occurs once. Could be a head, a tail, and a head. That's 2 heads. A head, a tail, and a tail. That's only 1 head, right? And let's go over here. Could be a tail, a head, and a head. That's 2 heads. A tail, a head, and a tail. That's 1 head. A tail, and a head. That's 1 head, right? A tail, and a tail. That's no heads. Right? So how many possible outcomes do I have for 3 coin tosses here? Got 8, right? The chances of getting 3 heads is 1 out of 8. The chances of getting no heads, in other words, 3 tails, is also 1 out of 8 possibilities. Does that match with what we've learned so far? Right? Okay. Does that match with what we've learned so far? 3 heads, the probability of getting 1 head is 0.5 times 0.5 times 0.5, or 0.125, which is 1/8, 1 over 8. That agrees with what we were talking about before. That independence events, if the probability of getting heads on each toss is 0.5 and they're independent events, it would be 0.5 times 0.5 times 0.5, or in other words, 0.125, which is the same thing as 1/8. That agrees with what we found before. What's the probability of getting 2 heads? Well, the probability of getting 2 heads is 3 out of 8, right? Or 0.375, right? Because there are 3 ways out of 8 possible outcomes, equally likely outcomes, that you could get 2 heads. What's the probability of getting 1 head? Probability of getting 1 head is 3 out of 8 again, or again, 0.375. Okay, and what's the probability of getting no heads? In other words, getting all tails, right? Probability of getting no heads or all tails, or in other words, 3 tails, is going to be 0.5 times 0.5 times 0.5. Remember those repeating independent events, a multiplication rule. So that again would be 1/8, right? Or 0.125. So if we were to add together 1/8, 3/8, 3/8, and 1/8, what do we wind up with? Somebody tell me. Wind up with 1. We have all the possibilities covered. These are the probabilities for each one of these equally likely outcomes. Okay, so we got 8 out of 8, exactly. And if you add up the fractions, you're going to get the same thing. They're also going to add up to 1 as well. So when you cover all the possible outcomes, the probabilities are always going to add up to 1. Okay, so now that happened because these are independent events. We're going to take another look at this from another perspective. You notice that as we got further out here, the less likely that the event was to occur. In other words, it's more likely that you're going to get these combination, these mixtures of heads and tails, rather than just get all heads. If I were to take another bounce, heads, tails, heads, tails, heads, tails, so on and so forth, we'd have, instead of 8 possibilities, we now be up to 16 possibilities. but there would still be only two ways to get all tails or all heads, right? So we'll get a much greater mix, but we we keep getting smaller and smaller on the extremes relative to the probability of getting some values that are in the middle. Now, that makes kind of sense. For instance, if you were at the roulette table and you were playing reds and blacks, right? And you'd say to yourself, probability of coming up red is, well, it's not really 50% because they have O and double O, those of you that have ever done this. So they actually make it a little less than 50%. But let's say for a moment it's approximately equal. The probability of getting even numbers or odd numbers, for instance, is the same, and you would get 50% of one and 50% of the other. Okay, the probability that if you were to do this 100 times, that the probability that you would get 50 heads and 50 tails is not insignificant. It's a reasonable outcome because it's 50-50 that you would get either one of them. It's actually not all that common. Maybe it only comes up about 25%, 30% of the time because there are so many other possibilities. But the single most likely possibility is 50-50. The second most likely possibility is going to be 49 of one and 51 of the other. Then the next is 48. So as we get to more extreme or unusual outcomes for this kind of binomial distribution, right? As we get to more extremes, like the probability of getting 30 even numbers come up out of 100 spins, that's pretty unlikely for that to occur with that big a number of spins, or 30 reds out of 100 spins and 70 blacks, right? That's not going to happen very often, and even less often 25 and 75 or 20 and 80. Those things all are going to occur less and less frequently, going to be rarer and rarer events. Okay, I got an example of that I'm going to show you. Let me take a quick look at questions. No, actually, they don't have to come in. We didn't define it. We just asked, what's the probability that if you flip the coin 3 times, that you would get 2 heads, right? So we look at all the possibilities equal, so that we didn't fix any specific order that they had to be in. Okay, so I'm gonna show you now something's called a Goaltend machine. A Goaltend machine is a device. Okay, this is kind of a sketch of it. The idea here is that, so I can, okay, I'm going to scroll down. The idea here is you have a reservoir up here where you take like balls, pinballs, or steel balls or marbles or something like that, and you drop them into this funnel, and the funnel is directed towards a pin. Think of kind of plinko or pachinko or something like that. It's kind of similar, right? Well, the deal here is that all these pins are spaced equally, and they're all spaced a distance apart that would encourage the ball to strike them and then hit the next one in the center, right? So the ball comes down, it hits this first pin. There's a 50-50 chance, maybe based on spin or maybe a butterfly off the coast of Africa or something like that, right? Some unknown factor could cause them to go to the left or to the right. 50% of the time you'd expect it to go to the left, 50% of the time you expect it to go to the right. So now, when it bounces off that pin, if it goes to the left, let me see if I can't get this to go away. Okay. If it goes to the left, it'll go towards this pin. Now it hits that pin. Now it's got a 50-50 chance of going left again or going right. Say it goes left again. Hits this pin. It's got to go left again. It may go left again, or it may go right instead. Well, as it descends, we would expect that since the chance is 50-50, it's going to be left-right. The most common outcome is for half of the time it's going to go to the left, half the time it's going to go to the right. So we would expect most of the balls to end up somewhere in the middle here. Now, sometimes it's going to go off to the left a little bit more frequently than the center, or go off to the right a little bit more than the center, and those will fall slightly to the left and to the right of the middle of these collection pans down here. But the probability that's going to go left, 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 right? That's going to be that's going to get less and less likely. So we would expect to see fewer and fewer balls going into these slots that are further and further to the left or further and further to the right, which would require all of the turns to be, say, to the right instead of to the left, if they're random. And in fact, if we scroll this back up and you get the view of it again, this is kind of the kind of outcome that we would expect to see. Now I'm going to play a video. I'm hoping that you're going to be able to see this video. I actually took this video myself at the Queens Museum of Science, right? I guess it's called the New York Museum of Science. I call it the Queens Museum of Science because it's in Queens. It's near Flushing Meadow, and they have all sorts of really interesting exhibits. This one is a example of that Goaltend machine. I'm going to turn my sound up. Well, no, I don't. You can. I'm not. I'm going to turn sound up. You may get a little bit of a feedback or an echo. I'm going to turn sound up so you can hear the audio as it's playing. So this odd-looking device is called a Goaltend Machine, or Queen Cups. It's located at the New York Hall of Science in Queens. As balls drop in from the top, they strike pins that are located in their cans. They have an equal probability of going to the left or the right of each pin. Watch as these balls follow the seemingly random paths down to bins at the bottom of the device. In the bins, we see a definite pattern taking place. Today, we're going to examine how such a seemingly random series of events could produce such a predictable outcome. Uh-oh. Oh, no. Okay. First thing I'm going to do right now is check to make sure you can still hear me. Can you still hear me? Because I had a little bit of problem. I had to force quit that video. Can you guys hear me? Okay, good. You're still there. I'm so glad. If we ever get cut off like that, just log back on. Like so. If that occurrence does happen, were you guys able to see that video, or see or hear that video? Okay, good. So you saw what happened there. It's that distribution took a characteristic shape. The less likely the outcome was, the lower the accumulation of balls. And if you notice, it formed that bell curve, that kind of normal distribution that we see come up quite a bit when the difference between measurements is mostly due to chance. And that's the case here. Whether or not the balls went to the right or left was mostly due to chance. So that's a demonstration of what we're looking at here. When we get into binomial probabilities, we're actually going to calculate these probabilities. Remember that problem we had with the 20% insured, 80% insured, 20% not insured? What's the probability that 3 out of, if we randomly select 10 people, 3 of them in any order at all would be insured and 7 would not be insured? We're going to have tools that we can use to solve a problem like that. Okay, right now we don't want to worry about that. And in fact, the formula that we're going to use or depend on to do that calculation is really complicated, because it looking at something like that Goaltend machine and trying to calculate all the permutations, all the possible outcomes that might occur, for each one of those bins that we're looking at. In fact, we're not going to do that. We're going to look at that formula. We're going to admire it. We're going to maybe try and understand it a little bit. We're not going to apply it, because it's, for any decent sized number of samples and outcomes, it can get very tedious and very difficult. We're going to use functions built into Excel or other software, or even statistical calculators that might be online or on a calculator you might hold in your hand. We're going to use those tools to solve those very simply and very quickly. Okay, so they're not going to be that challenging, but we're going to take a close look at it. We're going to learn quite a bit about how these things, these binomial possibilities, distribute themselves. Okay, so I'm going to move on from this. I think that we got enough of this for now, and we're going to be revisiting this at some point in the future. I'm going to close this. And they say don't save. Okay, I'm going to bring up another one instead here. Okay, so now one of the issues, I'm going to open up something that we were working on for the homework that confused a lot of people. I just want to go over this. Kind of a cheat. I know I'm giving you a bit more time on homework one. So this is kind of like a little bit of a cheat to, like, maybe bring this up and discuss it now. But I noticed a lot of people were a little bit confused about this. One of the things that we asked here, for instance, is we asked, what is the median age that a president was inaugurated, right? Well, if we count up all of these histogram bars, right? These are frequencies, right? These histogram bars are basically frequencies. This represents two presidents who are between 40 and 44. That would be probably Kennedy. And anybody know who the other was? Who was the other youngest president? What other president was 44 or under when they were inaugurated? Was Obama under 44? Clinton. Clinton was under 44. No kidding. That's I got a Clinton and Obama. I'm not sure which one it is. It's one of them, right? So at any rate, I don't think it was Clinton. I think Clinton was over 44 when it was inaugurated. I could be wrong though. So at any rate, but whoever it was, right? Two presidents up to that point had been under 44, were between 40 and 44. Five presidents were between 45 and 49. 10 were between 50 and 54, et cetera, et cetera. If you add all of these bars, the 17, the 5, and so you add all these together, you got 44 presidents. Yeah, well, that's the point. It can't be a single number, can it? Because if I were to ask you what's the median age of presidents at the time that they were inaugurated, all you know is it's the middle value, right? So if you have 44 people, your expectation was going to be somewhere around the 22nd or 23rd oldest president. Okay, well, let's see. You got two here, you got five here, that's seven. You've got 10 here, that's 17. 17 presidents were under 55, were between 40 and 54 when they were inaugurated, right? So now, if you go to the next bar, you have the 18th through the 17 and what I say, 17 and 7, the 18th through the 34th president are in here. So we know somewhere in here is the 22nd president. So really, you can't tell me what his age was. It could be that many of them were at the lower end of this range, and only one or two were at the higher end of this range, right? So they're kind of bunched up down here, but we don't know without knowing the individual values. All we can say is that the median age for a president within this group is between 55 and 59. It's conceivable. If if you wanted to, you could say to yourself, "Well, this is the 18th to the 34th. Maybe I'll attempt to interpolate this. In other words, 18 through 34. Well, that's 12 presidents. That's excuse me, 18, 20. That's 16 presidents are in this bar. 17 presidents are in this bar, and we're looking for the 22nd or 23rd. So that 22nd or 23rd would be six into this bar out of 17. So six out of 17, he's about a third of the way up. So maybe he's around 52 or 53. Well, we don't really know that, do we? Right? We can't tell that for sure, right? So we can guess that since he's in the lower third, that he would be closer to 55 than to 59. We can guess that, but we don't know that for sure. Could be all of these guys are 58 and 59, right? There's no way for us to know that. So the appropriate answer here would just be to say that the median age of presidents within this group was between 55 and 59. How about the 25th percentile? If 44 presidents, what presidents would be the 25th percentile president, right? 6 8 would be the 40 to 50, 40 to. Well, hang on a second. Now it was Teddy Roosevelt. Very good. I like that. It's great. Is that really true? Okay. Did you look that up? I'm going to assume that you looked that up. Okay. So now, actually, I think it's entirely possible Teddy Roosevelt's first term that he could be the other president that was in that 0 to 2, actually, because I think during his first term, I think he had two terms separated by a term when he wasn't president, and I think his first term he was very young. So at any rate, So he would be the 11th president, right? So where would be the 11th oldest president? 2, 5 to 7 presidents accounted for. So the 8th to the 18th president are in this bar. So the 25th percentile president would be between 40 and 54. Similarly, you do the same thing with the 33rd oldest president would be the 75th percentile, the top quarter, right? So 70 would be the 33rd president. Rather than count from the bottom, I might count from the top. So that would be, these are 10. So he would wind up in the same bar as the median would be, 55 to 59. Doesn't make much sense, but that's unfortunately the way this data is presented. The bars are relatively wide, so we wound up with the president that represented the 75th percentile and the median in the same bar as it happens. In fact, almost half of the presidents are in that bar, overall. Okay, so that's really kind of what we were looking at. So now I'm going to go now, and we're going to take a now. The next question. The reason why I brought this up is because the 25th percentile is the 25th percentile is the president whose age represents 25% of the other presidents are below him, and 75% of the age of the other presidents are above him. Similarly, the 75th percentile president is the president who has 25% of the presidents or other presidents are older than him, and 75% of the presidents are younger than him. And the age of the 25th percentile president and the 75th percentile president, that range is called the interquartile range. 50% of the president's ages are represented by the interquartile range. Okay, if we actually knew the numbers here, we can make this a little clearer, but we really don't know the numbers here. But now, the reason why I brought this up at this stage, 2 reasons. One is that there was a lot of confusion about this. And I think, like most of the old exams, and probably the exam I'm going to make up, probably going to have kind of a bar chart like this. So I wanted to make sure you guys understood it so you didn't it wasn't a curveball when you got it on an exam. But the other reason I brought it up is because there was another interesting question in there. And that was, what's the probability that a president is over, given that a president is over 50 years old, that president is also over 60 years old? Okay, there's still confusion. Okay, I'm sorry about that. All right, maybe you can back this up, go over this again, and after I post it, and it'll help clear up some of the confusion. But let's talk about this. Yeah, you got it right. That's right, Joni. But at any rate, let's look at this. How many presidents, given that a president's age is over 50, what's the probability that he's over 60? Okay, given that, what I'm saying there is I'm saying we're only going to look at presidents that are over 50 years old. How many presidents are over 50 years old? Well, I know this is 5 and 2 is 7 out of 44. There are 37 presidents in this bar, this bar, this bar, this bar, this bar. 37 presidents. So there's 37 presidents over 50. Out of those 37, forget about this guy because we say given that he's over 50, right? What's the probability that he's also over 60? Well, how many presidents are over 60? Well, we got 5, we got another 4, we got 1, we got 10 presidents over that are over 60. So the probability that given that a president is over 50, that he's also over 60 is 10 out of 37, right? So 10 out of 37 is about a little less than a third, 0.27 actually, 27% of the presidents that are over 50 were over 60 years old. Okay, so that was the answer to that. That was your first look at something called conditional probability. Okay, so now the reason why I brought this up is because we're going to look at this table for conditional probability. Okay, in this table, let's see what we have here. We have in the rows, we have gender, I have male and female. In the columns, we have marital status, single, married, widowed, divorced, and so on and so forth. This is marital status of U.S. population, 18 years and over in millions. So 29.7 represents 29.7 million people. right? Okay, so now let's take a look at this. At the time that this study was done, there were 200, actually it's a census. At the time this census was done, there were 214 million people that were 18 years or older in the United States. Probably wasn't too long ago, right? Because I guess the population now is 350, but there's a lot of people that are under 18 years old that are not counted in this particular census. Okay, so now let's take a look at this. What this tells us that 52 million of them are single, 126 million of them are married, 14 million of them are widowed, 21.7 million of them are divorced, adding up to our 214 million. We also know that there's 104 million males and 109 million males, also adding up to our total of 214 million people. Now, individually, within each group, there's gender differences. For instance, as far as males and females are concerned, there's more single males than there are single females. As far as married individuals are concerned, there's more married males than there are, just slightly more married males than there are married females, and so on and so forth. There's fewer divorced males than divorced females. Don't ask me how these numbers come up, but these were, I don't remember what year we didn't. I somehow or other somewhere along the line lost the reference to what year this was, but it was relatively genuine information. Okay, so let's say if one person is randomly selected from the whole 214 million in this population, right? Find the probability that that person is divorced. Now, I'm not going to ask you to tell me the fraction, just the formulas, right? Because the probability is going to be almost always going to be a fraction. How many out of how many? It was a probability. Okay, so the probability that a person is divorced out of the entire population. Well, the bottom of that fraction is going to be 214, right? Okay, so how many people are divorced? 21.7 million out of 214 million. So the fraction, the probability is going to be 21.7 over 214.2. Exactly. Divorce total over the total, right? That makes sense, right? Nothing wrong with that. Nobody said anything about male or female. We weren't breaking it up that way. We are just interested in overall the probability that a person is divorced. Find that probability that that person that's divorced is a male. So what's the probability that a divorced person is male? Well, hang on a second. Okay, probability. There's two ways you could really look at this, right? One way is, well, hang on a second. That 104 over 214, that 104 over 214 is the percentage of males, the probability of being male in the population. We want to look at the probability of being divorced, right? So the probability of being divorced in this population, if we're just looking, what's the probability of being randomly selected and being a divorced male, it's going to be 9 million out of 214 million, or 9 out of 214. Okay, another way to look at this, which is find the probability. We were looking at only divorced people in the sentence before, right? Find the probability that that person that's divorced is male. Well, there's 21 million people that are divorced. The probability that if you randomly select among only the divorced people, that's going to be 9 out of 21.7. Okay, I think we really had intended for that to be the probability that if you randomly selected a person that person would be male and divorced 9 over 214. I think is really what we were looking for. But it's not that clear, I guess. Could be clearer. Find the probability that that person is both male and a widower. What's the probability if you randomly select a person that they're male from this population, that they're male and a widower? Okay, well, we're only looking at males and we're only looking at male widowers. So the probability that that person is a male widower is 2.7 out of 214. Okay, 2.7 out of 214. Wouldn't the second one be, let's see, 9 out of 21.7 over 21.4, 9 over 21.47 over 21.4. 214.2, which is 9 over a tenth. Well, you never get a possible, Jonathan, if you did that, you would get 9 divided by something that's roughly 1/10, right? Which would be 9 divided is 90. So you're never going to get a probability that's greater than 1, right? So just, I think you're getting too far ahead. Yeah, B refers back to A. But I would reword this and just say, what's the probability that a randomly selected person is divorced? Find the probability that a randomly selected person is male. That's much clearer, isn't it? Because the probability a randomly select person is male is going to be 104 over 215, right? As you guys said before, if we clarify it that way, that's what that would be. Probability a randomly selected person is divorced is going to be 21 million total divorced people at 215 million total people. Find now the probability that a randomly selected person, again, we're going to go back in there and just randomly select someone. I like this better. This is better wording. Is both male and a widower. Okay, I'll leave that up to you. Tell me, what's the probability that you randomly select a person from this population and he's both male and a widower? Okay, that one's, we're getting a little bit clearer now, right? 2.7 over 214.2 million. Okay, now we're going to get back into what we called conditional probability. Given that a person is male, what is the probability that he's married? Okay, so now we have a condition here. First, we have to start with the assumption that a person is male. So none of the people in this row are going to be part of what our calculation is. This is a conditional probability. So we're really only dealing with 104.9 million people, not 214 million people. Given that the person is a male, given that that person is male, what's the probability that he's married? Well, out of 104.9 males, 63.5 million are married. So the probability, given that a person is male, probability that he's married is 63.5 over 104.9. Okay, does that make sense to you guys? Are you guys reasonably comfortable with that? Over, let's see, at tilde over 14, population focused on is only the width. I'm not sure what that means, Jensen. Oh, yeah, you guys having conversation. I never had that experience before. Usually, the only people that are, are chatting back and forth are me and the participants. I'm really pleased that you guys are having your own conversation here, in the background as I'm doing this, but you're answering each other questions. I really like that. That's really new. I like that. Keep it up. Yeah, yeah, Jensen, the yeah, we're gonna take a short break right now, and I'll tell you what, Jensen, at some point maybe we can email back and forth, and we can go over it a little bit again. Okay, so I would say let's stick with the descriptions that we used here, where I changed it to randomly selected person. I was a little bit more specific on the questions, and I'll make sure that if any of this turns up on a test or something like that, it's as clear as I can possibly make it, so it's not like a real curveball or something like that. Okay, so at 7:45, let's take a 10-minute break, and we'll come back, and we'll run. I have some more material I want to go over, but it won't take all the diagnostic tests. Let's take 10 minutes, and we're going to come back, and we're going to do something really kind of interesting. It's an evaluation of how diagnostic tests work. Okay, so we're back at 7:55 on the button because we want to be on time for that because I need at least a half hour to go over that. Okay, you guys are still having a conversation here that doesn't involve me. That's very good. I haven't had that experience too much. Okay, so you guys got that, right? 755, you coming back? Uh, okay, good. That's a good question. Go back. I'm going to post a video afterwards. You can go back over it, and I'll tell you what. Before the next exam, I'm going to have a session where you guys can email me and ask me questions about specific areas you have. Like, for instance, this conditional probability stuff, or dependent probability, and so on and so forth. Independent probabilities, and so on and so forth. And that you can go ahead and review that. Can you answer your question? 25th percentile is okay. I'll bring that up. Hey, Rebecca, the 25th percentile president out of 44 presidents, what number president is that? If we put them in order, the youngest to the 44th to the oldest, that would be number 11, correct? So where is the 11th oldest president going to be? Well, the two youngest are in 40 to 44. The seven youngest are between 40 and 49, right? And finally, the 11th is in this bar here somewhere. So the 11th, the 25th percentile president would be between 50 and 54. He would be in this bar here, the 11th oldest guy, because seven of them are here. And if we fill up this entire bar, we got 17. So the second oldest, the seventh oldest, and the 17th oldest, right? Well, this means that this bar represents the 8th to the 17th oldest. So the 11th would be in this bar somewhere. So he'd be between 50 and 54. If we had the real actual ages for all of these presidents, you would actually be able to sort them, count down from the youngest to the oldest, count down 11 presidents, and actually pick out an age, right? Or if you wanted the median, count down to the 22nd or 23rd, and you would have an actual age. But that's not the way this data is displayed. That's not the way the data is presented to us. If we had the actual numbers, you can have an actual age. But since we don't have the actual numbers, you can only describe it as the location of the bar that that president is in. Similarly with the median and the 75th percentile. The 75th percentile was the 55th to the 59. It happened to be the same bar that the median was in. That's because so many of the presidents were between 55 and 59 years old. Yeah, he's the 33rd president out of 44. Okay. You could count up from 33, or you could count down from 44 to 33. Either way, you wind up in this same bar. Okay, so we're going to take a break. That's breaks. I'm going to let you chat.